Let's calculate the final volume of an isentropic piston process. Now you can imagine this could be sort of arbitrarily difficult, but the nice thing is, we're given that it's isentropic, so some sort of piston, we're also going to deal with an ideal gas. So if you have an ideal gas and you know K, the ratio of its specific heats, in this case 5/3, suddenly these problems become very easy. There are simple ratios you can quote from your lecture notes. You can do the calculation in 1 minute. Let me show you. So imagine that we're given an initial condition of 300 Kelvin and 1 cubic meter for the temperature and volume. We know that the final temperature is 400 Kelvin, and we want to know the final volume. Okay, how do we do that? Well, let's quote one of these ratios from our lecture notes. T2 over T1, again for an isentropic ideal gas, is little v1 over little v2 raised to the power k minus 1, where again, k is the ratio of specific heats of the ideal gas. It's fixed though, and in this problem we know it's 5/3. Okay, so we want to solve for big V2. Well, the nice thing is little v1 over little v2 in a piston must also be equal to big V1 over big V2, right? The mass is fixed. Okay, so we can do that. And guess what? We know all of the variables in this expression except for V2, so let's just solve for V2. To do this, you have to do a little algebra, and so we raise both sides to the 1 over k minus 1 power to move the power over to the left. Now we just rearrange to solve for V2, so V2 is V1 divided by that whole temperature ratio thing. Just so we don't have nested fractions, maybe I'll move that up and then take the reciprocal of what's in the denominator. So now we just have one fraction to deal with. Okay, so now we know all the variables. Let's put them in. So the value of V1 is just 1 cubic meter, T1 is 300 Kelvin, T2 is 400 Kelvin, K was 5/3. Carefully enter all of that into your calculator and you find that V2 is just 1 cubic meter times 0.65, which is 0.65 cubic meters. So that's the final volume of this isentropic piston process. And the nice thing was, since we had an ideal gas and knew it was isentropic, we could just start with that simple ratio. We didn't have to do any explicit entropy balance, which tends to be a lot harder for problems like this.